Okay, so we are here in the third part of the webinar series, Statistics and Data Science. We started 2 weeks back with exploratory data analysis, where we talked about how to analyze your data and look at cleaning your data. And last week, we talked about data and sampling distribution, where we talked about various sampling techniques and how the various data distributions that are present in statistical analysis. And today we will be talking about statistical experiments. And going forward, we'll be getting more into statistics in machine learning starting next week. I'm excited about it. And if you have missed our webinar 1 and 2, here are some links. So we have the entire collection for our webinar 1 ready, while we are waiting on some links for webinar 2. We will post them soon. If you have downloaded the slides, you would have access to this as well. And a huge shout out to our volunteers. My name is Sneha Thanasekaran, and we also have Shivya, Aryan, Soumya, Sahana with us today. They will be leading the Q&A, and if you have any questions throughout the webinar, you can post them in the Q&A box. And a huge shout out to our sponsors. They are encouraging partners who currently have job openings in data science, so make sure to check them out in their careers page. And lastly, I also want to thank you all for your feedback on webinar 1 and webinar 2. We have made so many tweaks and changes based on those feedbacks, so thank you. And please make sure by the end of this webinar, you submit your survey questions. And before we begin, if you have downloaded the slides, you must have a link to Collab Notebook here. All you have to do is click on it for the link to open. In the meantime, Shivya will also share the Collab link on the chat. So make sure you click on it and open your Google Collab Notebook. And finally, to talk more on today's session. So this session is focusing on statistical experiments and significance testing. I'm proud to have our speaker, Angela Gaetano. She is a data science manager for a diabetes medical device company in San Diego, and she obtained her bachelor's in mathematics from Belmont University and her master's in data science from Lipscomb University in Nashville. Applied statistics has been a top interest throughout her career, both in healthcare tech companies as well as in academia. She enjoys focusing on solving real-world problems using a combination of application techniques and project management expertise to deliver high-impact, low-cost solutions to businesses in healthcare. I'm proud to say that she is also my manager. And today she will be talking about a lot of topics of why statistical experiments are important, hypothesis testing, and A/B testing. Hypothesis testing and experiments are a critical part of a data scientist's job. And she has put together a very fun-filled notebook with a lot of exercises. I'm excited for this webinar and happy to have you here, Angela. Thank you, and take it away.
Hello, everyone. Thank you, Sneha. That was a great introduction. So thank you for that. Thank you, everyone, for joining us today, being with me to share my passion and interest in statistics. My goal today is to not so much, make you all advanced experts in the mathematical principles behind statistics necessarily. It's more to give you some very useful practical tools that you can basically take with you immediately right after this session. I want to give you some tools and methods that you can use in your day-to-day lives, either as aspiring data scientists or as existing data scientists in your roles. I think that statistics is one of the great tools because by just learning some of the basics, you can accomplish great things and contribute to the broader scientific community. So with that, I will share my screen. and you should all now be seeing the notebook. Can someone confirm? Great. Thank you, Sneha. All right, so yes, again, welcome. I just wanted to give a shout out to a few co-authors to this notebook. Sneha, Somya, and Shapiro all helped with some of the pieces of this Jupyter notebook, of this collab notebook. Got disconnected there, including peer review and even adding some content. So thank you all for that. I've also included a link to the Google Drive that contains all of the data files that will be used in this notebook. So if anyone's interested in playing around more with those data files, you can go to this link and download them. For the purpose of this notebook, I have configured it so that you don't need to separately download them to be able to run the code in this notebook, but feel free to take a closer look if you would like at a later time. So a bit more details on the topics that will be covered today. First, as an introduction, why run statistical experiments? What's their importance to the mathematical and scientific community? Secondly, variability and estimates. It's really important to understand that statistics is what bridges mathematical principles with more natural real world data. And in that bridge, a lot of variability is going to be introduced, and it's the principles of that variability that is the foundation for a lot of traditional statistics that we'll be covering today. So I think that's really important to cover. And then probably our biggest topic today is hypothesis testing, traditional hypothesis testing. I will be providing a step-by-step guide to the standard hypothesis testing framework. This is kind of a step-by-step process that you can use for almost any traditional hypothesis test to help you get from beginning to end with any hypothesis test that you would like to perform. One key piece of that framework is to choose the appropriate statistical tests. There are so many different statistical tests to choose from, and which one you choose varies depending on your circumstances and the data that you are working with. So kind of on that note, we'll be discussing how you can test for assumptions for various statistical tests. And of course, we'll be talking about how you can interpret the results, this meaning of significance of a hypothesis test. So the two kind of main categories of traditional hypothesis tests are parametric and non-parametric. So some of the parametric tests that we will be discussing and covering today include t-tests, ANOVA tests, and chi-squared tests. I understand if any of you participated last week in the series session, chi-squared tests were introduced at that point. So I think going over it again here will help kind of solidify some of those concepts. And then finally, for non-parametric tests, which can typically be a little more tricky to understand, we will discuss several of those as well to hopefully help you navigate that space. This will include touching on the Mann-Whitney test, Kruskal-Wallis, and Wilcoxon signed rank tests. In addition to kind of your basic hypothesis testing framework, it can be really beneficial to add additional evidence to your study and to your experiment in various forms. A couple of ways you can do that I'd like to cover in today's session are this concept of resampling, and specifically in permutation testing, which is basically a way to prove that your sample is a good one, is a good representative sample. And then secondly, not only do you want significance for your hypothesis test, but it's really helpful to add the layer of the power of your hypothesis test. So we'll be discussing how you can set up for power of a hypothesis test, and also how sample size can influence the power of your test. And then finally, we will be touching on a real-world application of statistical experiments, which is most commonly found in the industries of software development, web development, and UX design, which is A/B testing. This is a section that we'll be covering at the very end, and I did get some help from Sneha and the other volunteers in introducing this concept for you all. So that's the overview. We will be taking our midway break during the hypothesis test section, so I'll be sure to call that out when the time comes. Okay, so for our introduction, why run statistical experiments? So kind of as I mentioned before, statistics and statistical experiments is a very attainable tool for the everyday data scientist. But not only is it attainable, it's very powerful. The more you learn about these concepts, the more you will see them kind of in your day-to-day lives all around you. And you'll be able to actually get evidence-based answers to some questions that you might even have about some real-world data and real-world circumstances. By leveraging principles of mathematical probability and inference, which you may have gotten some foundation in attending last week's session, we can provide answers to very meaningful questions that would otherwise be impossible to answer in our world of large numbers and possibilities. And just to kind of expand on that, from the mathematician's perspective, mathematicians speak in absolute truths and in axioms, and in that regard. And whereas statistics is all about, estimation. So what these principles will help you do is to apply these truths of mathematical principles to get real answers about natural real-world data. And I think that's fascinating. By finding ways to harness samples to represent these broader truths and these broader populations and themes, we can continue to advance the learnings of the scientific community. Some say data is power, but for me, it's a little more than that. I would say statistics with power is significant. So data on itself, not so much, but if you can apply some basic principles of variability and estimation, you got something very, very powerful and significant.
I'm sorry to interrupt you here, Angela. Your mic is not very clear. There's some disturbance coming in.
Oh, let me see if I can fix that.
Oh yeah, perfect. I think it's
is that any better? Yes. All right, I just turned it a little bit. Perfect. Thank you for letting me know.
Sure. Thank you.
Sure. All right, so not only will this lesson hopefully enable you to run your own statistical experiments at will, but it will also empower you to look at the world with a more scientific eye. You will be able to read various clinical studies and do your own literature reviews and understand what they're truly saying and what the claims they're making are, and what you can extrapolate from those. For example, with these kind of basic concepts of statistical experimentation and hypothesis testing, anyone can begin to better understand real-world situations such as, the clinical trials for the COVID-19 vaccine for Moderna and Pfizer, and how to interpret those results. So understanding these will help you, make your choices and be a participant in society. So I think it's very important and just can propel a data scientist forward into a new realm of understanding what data truly means. All right, so moving on, we'll briefly discuss the principles of experiments. There's 4 key pillars, I suppose, of experiments. The first one is controlling. So you have to control for differences between your groups other than what is being tested for. Because of course, if there are other differences that you're not testing for, you can't make any claims that the differences that exist in what you're testing for are for a particular reason. It could be because of a number of reasons that you are not controlling for. So that's
one of the top key principles of experimentation. You'll often hear, about a control group kind of representing this principle. Secondly, you have randomization. So randomization helps account for uncontrollable confounding variables also. So it's important to realize that you can't always perfectly control for all of the differences between your groups and your experiment. So one way to account for that is to get as random as a selection as possible so that the differences that do exist are equally represented in each group so that you can expect the same mix of differences in each group. Randomization will help you with that. Next, you have replication. So this is the concept of being able to perform your tests multiple times, whether that means sending different subjects through a similar experiment in the same exact way, or if it means replicating your entire study. If you perform a study, next month, you should be able to perform the exact same study with the exact same structure in 12 months. And that's, obviously important for solidifying your evidence. And then finally, there's the concept of blocking. So this is the intentional grouping of individuals with common uncontrollable confounding variables, and then randomly assigning equal numbered subsets into the treatment groups. So this is basically a more hands-on approach to accounting for these uncontrollable confounding variables, whereas randomization is kind of more of a principle of if you select randomly, then you're going to assume you're okay. Blocking is if you're very aware of a specific difference that is present, you might want to take a more hands-on approach to making sure that that difference is equally represented in each of your treatment groups, each of your experimental groups. So this is the common principles you may hear about if you're reading any kind of clinical trial or a protocol for a study. These will often be mentioned in how they accounted for each of these principles or how they accounted for confounding variables. So that's usually documented as part of the study. All right, so getting more into some of the principles of statistics that will lead into hypothesis testing, we'll talk about the variability in estimates. So the key word of the day, I think, for this, for today is the point estimate. This is the sample estimate that is the measure of the population parameter. So it's your way of saying, here is my representation of a broader truth in a particular measure. So for example, you may have seen the notation X bar, which is the point estimate for mu or the population mean, or you may have seen P hat, which is the point estimate for P or the population parameter for proportion. So the point estimate will vary each time you take a new sample of your population. And this difference between each point estimate of every sample is basically the sampling variation. You can't get the same exact sample with the same exact values every time. Very rarely can you even get that twice, right? So the idea here is that if, for example, if you were to flip a coin 50 times, the proportion of heads to tails may vary each time you do this test of 50 coin flips. And that proportion each time is your point estimate for a broader truth of your population proportion, which we know the probability on a population level for a coin flip is 50% or 0.5. So if you were to take samples and measure this point estimate many times over and over and over again, perhaps in a simulation is one way to kind of learn this concept, you will actually build up a distribution of your samples. So this is called the sampling distribution of the point estimate. This image here I think is a great visual example of this. So on the left, you will see your population distribution. So this is the theoretical full population of whatever value you're trying to measure, right? And it has the shape. If you were to take a sample of size n out of this population, measure that sample's mean, which is the point estimate x bar, and create and plot that in a new population distribution, do that over and over again and build out your population distribution, that distribution is your sampling distribution of the mean. And it's this distribution that ends up being the foundation for for really the entire principle of traditional hypothesis testing. Another key fact about this distribution, the standard error of the estimate that you may have heard of in previous sessions in this series is actually the standard deviation of the sampling distribution. So if you know that the standard deviation is a certain distance from the mean on either side of the mean here, if you were to measure the standard deviation of the sampling distribution, that is your standard error of your estimate. So typically in real life, you're not going to take multiple samples. That's just not practical. That's why we do statistics, is so that we can take a sample and make inferences of the population. If you only have a single sample, then you can use this equation to actually measure the standard error rather than sampling infinitely many times and taking the standard deviation for that distribution. So here is your more practical formula for that. If sigma, or the population standard deviation, is unknown, which is most of the time, in my opinion, you will use S in that position rather than sigma. S is your point estimate for the standard deviation. So the standard deviation of your data divided by the square root of the sample size of your data. All right, and that is variability and estimate. So going forward, if I show you when we talk about p-values, for example, we will be talking really in the context of the sampling distribution, not of the population distribution itself. All right.
Angela, on that note, there's some, the mic is catching a lot of disturbances. Do you mind resetting it a little bit, please?
Yeah, sure. Mm-hmm. Is it like background noise or?
Oh, no, I think it's you're breathing into it a little, so maybe.
I see, okay.
Yeah. Yes, for now, yes, I think so. So in case there is, I will remind you, but for now it's good. Thank you.
Thank you. Okay, that sounds good. Okay, so moving right into hypothesis testing. So as an introduction to hypothesis testing, the hypothesis testing takes the position of the skeptic. So the mindset for this is, I will not be convinced that there is any difference unless strong evidence is present in favor of that difference. It's kind of a concept of innocent until proven guilty. So formal testing using p-values, there's a few key concepts to cover here. The p-value is the probability of observing data at least as favorable to the alternative hypothesis as our current data set, if the null hypothesis is true. It's kind of a lot to unpack, but I think this image will help with that. So this distribution here, you can think of as the set of possible results under your null hypothesis. So you assume the null hypothesis and you statistically build a probability distribution around that hypothesis. So you'll see that the true value under the null hypothesis of this population measure is going to be right in the center by design. Okay, so this is what you're testing against using your sample. Now, the idea behind traditional hypothesis testing is to say that if the point estimate of your sample is so far in the tail of your probability distribution of the null hypothesis, then we're going to assume that that's too unlikely to actually prove out the null hypothesis. Like if your value is so far in the tail, then this hypothesized probability distribution is probably not true. It's probably going to be closer to that point estimate. It's probably going to be shifted. So that's your way of saying, I'm going to assume a probability distribution. And if my result says that that's very unlikely for those differences to exist between the null hypothesis and what you are actually measuring, we're going to assume the null hypothesis is wrong. So the p-value is actually the area under the curve of the tail. So the lower the p-value, the stronger the data favor the alternative hypothesis. So generally, you're looking for very small p-value. And as part of your study design, you set a significance level for your study. Usually it's notated as alpha. And 0.05 tends to be the most common significance level used. I know I've asked the question before, why 0.05? You know, it's why that number and not 0.04 or 0.07 or whatever it is. It turns out that while this number is somewhat arbitrary, it has been proven out in many trials to be the most common kind of natural threshold for human skepticism. I've included a link here that includes an exercise that kind of proves that out, to say what you can go through a personal exercise to see what is your threshold for skepticism, and it almost always is going to float right around 0.05. Just kind of interesting exercise, can be fun to do. So if we are going to set a 0.05 significance level, that is basically the threshold where we are saying if the probability of our point estimate being in this distribution is less than that, it's that far into the tail, then we're going to say the null hypothesis is wrong and this assumed probability distribution is not true. So we want a p-value or a area under the curve that is smaller and further into the tail than this threshold of 0.05 area under the tail, area under the curve. So that's kind of the principle of it. I know for me, you know, it took an entire semester of a course to really understand this key concept. So, you know, continue to think about it and read up on it. If you get it right away, though, that's great too. I hope that helps. Because the next step is to discuss the step-by-step practical guide of hypothesis testing. This is what I use every time I'm setting up a hypothesis test. So we'll go through these one by one and explain. Okay, so step one is always to define the null and alternative hypothesis. The null hypothesis is always the one that contains equality. The alternative hypothesis implies inequality, or usually this concept of a difference from a particular value or a difference from another sample, another value. Then you will be setting the significance level alpha. 0.05 is more commonly used, I would say, just in my experience. But feel free to use 0.01 if you want to make your test more strict. You want to allow for a little bit more of rare probabilities in your test. But for the purpose of this, we will be discussing using 0.05 throughout. Step 3 is often the hardest, and it is to select an appropriate statistical test. So a couple key things is to consider the type of data that you have in your study. many questions will come out of this that we will discuss more in depth later with some exercises. One is, how many groups of data do you have? Another is, are your data paired together, or are they completely independent groups? Also, you want to ask yourself, what's the output data type? What's the data type of your output that you're trying to measure? Is it continuous, binary, or categorical? The other important concept for choosing a test is understanding the assumptions needed for various tests and whether you need to test for those assumptions being passed. The most typical assumptions of a parametric test are that your samples are independent and unbiased. If you're sampling in a simple random fashion, taking simple random samples, then that is probably pretty likely covered. There are other tests you can do to prove that more efficiently. But as long as you're doing true randomization, you're probably okay, at least for an initial run. Additionally, the other common assumption is that your data is approximately normal within all groups of your hypothesis test. You can use, there are various tests for normality. I think the most commonly used ones in my experience are the Anderson-Darling test or the Shapiro-Wilks test. However, if the sample size is large enough and the data appears to be approximately normal, which you can kind of, look at visually or using descriptive statistics, there doesn't seem to be any significant skewness, then there's no real need to test this assumption. There is some flexibility in a statistician having some level of judgment in this, just kind of making a judgment call. With certain level of expertise, that's typically accepted, but it never hurts to run the tests as well if you want to be safe. If there is more than one group of the data, and depending on what you're measuring, it may be important to know whether the variances between your groups are equal as well. That's another assumption that commonly gets overlooked. So for this, again, number of tests you can use, but the most common, I think, and useful I've seen are the F test or the Levine's test. The Levine's test is a bit more conducive to data that is not normally distributed. This is something to keep in mind, but F test is kind of your go-to standard test for equal variance. Next, you need to decide if it's a one or two-tailed test. A one-tailed test implies that the alternative hypothesis is a directional inequality, that you're testing that something is greater than another thing or less than. Only use the one-tailed test, though, if the intention of the experiment is based on a pre-stated suspicion of a directional inequality. That's often not the case. A lot of the time, you're just checking for the presence of some kind of difference. So I'd say the assumption, and in a lot of statistical functions and in scripting, you'll see that the default value for this parameter is two-tailed. It will assume you're doing a two-tailed test. Two-tailed tests are the ones where the alternative hypothesis is not equal to. Next, of course, you'll run the statistical test. Often this can be the easiest part. It can usually be done with one line of code or, depending on the tool you're using, one or two clicks. And it simply takes in your data and then a few testing parameters that you have defined from these previous steps. And finally, of course, you'll need to interpret the output and decide whether to reject or fail to reject the null hypothesis. And this is where you will use the p-value to do this. If the p-value is less than alpha, or your significance level, you will reject the null hypothesis, proving the alternative. Otherwise, you will fail to reject the null hypothesis, which technically just conveys that there was not enough evidence to reject the null. You can never really, maybe never is too strong of a word, but typically you don't prove the null hypothesis. You just either reject it or you fail to reject it. So that's kind of the terminology for the interpretation of the hypothesis test. All right, and the next step, I want to go more in depth on the step of choosing the appropriate statistical tests. So there's certain key questions involved in this. I've kind of articulated out the most common ones, but I've also included some visuals that a colleague of mine went through an exercise to help create to provide a really practical, easy to use tool to decide which hypothesis test to use. It can get fairly complicated, and these things aren't really, I'd say this is a very good representation of your standard hypothesis tests. Some of these can be slightly debatable. In statistics, there can be some flexibility in approach, but this is going to be, in my opinion, the best representation I've seen of using standard principles to choose your hypothesis test. There are two images here. One is for if your input is a binary variable, and one is for if your input is a categorical variable. We'll talk more about continuous here in a second. So some key questions. What is the data type of your response? What are you measuring? Is it continuous, binary, or categorical? And of course, what is the data type of your input? A binary input implies that you're dealing with two groups, group A, group B. So the input is which group is this subject, is this record in your data in? And categorical input implies you have multiple groups. Continuous input implies that you're interested, typically implies that you're interested in correlation. So if the input is binary, you want to ask, and your response is continuous, which is very common in hypothesis testing, you'll need to ask if the data are paired. And by paired, that means that the two groups are dependent. They belong to the same subject in some way. Typically what this looks like is a before and after study. If you have a subject of a trial or a participant of a trial, there's probably a before measure and an after measure, but those two values are paired because they're dependent. They're not independent, like randomly from two different groups. You also want to ask if it's binary or categorical, whether the variances are equal between the groups. We mentioned that briefly earlier. And if the input is continuous, you will likely be running a correlation test. Here are some different correlation tests to run. It kind of varies depending on whether your data passes a test for the assumptions of these tests. So this is the parametric correlation test, and these are non-parametric. So again, you need to ask yourself, do your data satisfy assumptions for a parametric test, or do you need to choose a non-parametric test? So I have these for reference. I'm not going to go through them in detail today, but feel free to look through them. It can take a minute to kind of wrap your head around it, but it's a great tool. I use it all the time to help me make my decisions. All right, so let's start some examples, try to put this together. So some key packages here that we will be using. The stats package and the scipy package is probably the one I most commonly use when dealing with Python. Typically, I'm either using this or I'm using R. So for the purpose of Python, we'll be talking about scipy stats, and then I'm dealing with data frames with a pandas package. So first exercise, I'm going to ask the question, are mean crime rates different between the North and the South? Imported the data here, and you'll see that there's a variable called crime rate. And there's also an indicator for whether that crime rate belongs to the South. So if it's 0, I'm assuming that means it belongs to the North. If it's 1, it belongs to the South. So let's go through our steps. Step 1 is to define the null and alternative hypothesis. So the question was, is there a difference? So I'm going to say, is the difference between the North and the South, difference in crime rate, which is mu, is the population mean crime rate for the North different than the population mean crime rate for the South? The null is that there is no difference, or the difference is 0. The alternative is that there is a difference, and that it is not 0. We'll use our common alpha's 0.05 significance level. And now we'll select the appropriate statistical test. So first, what type of variable is the input? The input is a binary classification of North versus South, so the answer is binary. What type of variable is the response? The response in this case is crime rate, which is a continuous value, as we can see from the data here. Is the response paired? The answer to this is no. They're not paired because these two groups are independent. You have a group of crime rates from the North, a group of crime rates from the South. There's no interaction there. And then finally, does the response follow a normal distribution in both groups? So let's take a look at this. We may need to test for normality, or we might be able to assume normality based on just kind of looking a little deeper at the data. So the first step that I often use is to just describe the data. Build out your basic descriptive statistics and take a look, and I'll explain how to interpret this. So first, I am filtering for the Southern data records, and then describing those. So some things that jump out at me. The count is 16, that's kind of low. So if it's generally, if it's under 30, this makes me take a closer look, basically. That's kind of a red flag. Now I'm going to compare the mean and the median, which is the 50% percentile. If they're pretty close, that's a good indicator that your data is fairly centered. And they're only about 1 value apart. Another thing I'll look at is I'm going to compare the max to the mean and the min to the mean. So the min to the mean is about a 44 difference in 44, and the max to the mean is about 45. So all this is telling me is that everything's centered really nicely. Despite the count being low, this looks like I can assume approximate normality of this data. Let's do the same for the North. All right, so we have a slightly higher count. Mean and median are very close. Difference between the min and the mean is about 50. And the mean and the max is about 56. That's pretty close. So my conclusion is that we can tell the data are very centered, not skewed. And the samples, even though the sample size for the South is questionable at 16, I'm gonna say I can assume normality. No need to test here. So now that I know that my data are normal, I'm gonna ask, are the variances between the groups equal? This is an important parameter for a test comparing two continuous variables. So I'm gonna run an F test. You can use the stats package. There's an F one-way test. And I'm just going to throw in the arrays of the North crime rate and the South crime rate. See the p-value printed out here. It's much greater than 0.05. We failed to reject the null. In these tests for assumptions, the null is typically that the assumption is satisfied. So the variances are equal is the null hypothesis, and we failed to reject it. So the appropriate statistical test to test our original hypothesis is a student's t-test. Yay for normal, easy data. This is what we want. It's very easy. We also decide that since we're just asking if there's a difference, we're going to use a two-tailed test. So we'll use the student's two-sample t-test, which you can run, again, simply passing in both arrays. I didn't have to specify the tail because the assumption is that it's a two-tailed test. You'll see that the p-value is very high again. So we failed to reject the null. There is no difference in crime rate between the northern and southern regions.
All right, so that was that was a simple example, and we'll get into some slightly more complicated ones in the second part. And this is our break. So Sneha, you can take it away.
Awesome. Thank you, Angela. That was very informative, and I'm sure our audiences are enjoying it. I do have this question for you. For someone who is a beginner who is starting into statistical analysis, they're saying they are hearing the topic of hypothesis testing and p-value for the first time. So they're asking, how would you encourage them to get better and better in statistical testing?
Yeah, great question. So an example of a situation where you might be trying to jump right into more predictive modeling and machine learning. And if your interest is more to go that route as a beginner, I'd say it's still important to understand hypothesis testing, because often you will use hypothesis testing to either prove or disprove the strength of your model. That's not always the chosen method, but especially for regression models, you'll often get a p-value for your regression model, and it tells you whether basically the variables in your model are significant. So there are a lot of great books on this. There's a lot of great websites on this as well that are great at walking through. Statistics How To is a great site that I often use when I forget some of the more basics that I can go to. But yeah, I would say, with the workflow chart in here and understanding some of the principles of p-value, I think you can get very far very quickly.
Sounds good. Thank you. The next question I have is, if the input is binary and response is categorical, does it always mean it's always paired? So I want to answer that question, if you don't mind, while you take a break. I'm sorry.
No, that's great.
So paired means usually both the samples are from the exact set of objects. For example, if you're testing something like a pre and post, like before the drug and after the drug, then you would probably be testing the 20 users who did not use the drug before to 20 users who used the drug before. So in that category, the 20 users are the same users, right? And that is what it means when they say paired samples. So that is different from binary and response variables and categorical variables. So paired means paired relates to the samples itself. Yeah, if you're going to add something up to this, feel free to.
Yeah, just one thing to add. I think the beginning of that question was if the input is binary and the response is categorical. We will be covering an example of that specific characteristic later. So yes, that might help as well.
And the other question is there a way to compensate for the differences in size between the two groups?
The difference in what? I'm sorry?
The sizes of the sample sizes between two groups.
There is. So you can do things like imputation to basically increase the sample size, where there's a lot of different methods for imputation, but you can basically duplicate certain records so that you get a slightly fuller data set. That's usually more needed in the space of when you're using data to build models, predictive models. Typically that's not needed in basic hypothesis testing, just because there are enough strategies and approaches that accommodate for the smaller sample size, such as non-parametric tests. So there's not usually a need to even out the samples.
Right. Yeah, it makes sense. So there's this other question that says, I'm not understanding the question, so we will definitely like your input on this. Let's say you have a large sample and want to compare means, do you ever use a z-test for a difference if the variance is unknown?
That's a great question. I haven't, but I think if your sample sizes are large enough, and you can run like a QQ plot to see that it's normal, I'd say only in that case would a z test be appropriate. It would have to be very, very normal. But yes, I mean, if your sample size is large enough, the difference in result that you'll get between a z-test and a t-test are not going to be that different.
Great. I think we'll stop here. The rest of the questions will be taken care of our Q&A leads in the background. Angela, you can continue with the presentation. Thank you so much. And everyone gives a thumbs up if you like the Q&A session. Thank you.
Yes, thank you all for your questions. All right, so moving right along to more exercises. We'll be switching to a different data set, a pretty famous instruction data set called the Titanic data set. You may have used this for some training in learning machine learning models as well. We will also be using this for the sake of familiarity. You'll see I've read it in from the Google Drive and have printed out the full data set. The question I want to ask is there a difference in ticket fare between the survivors and the non-survivors? So let's scan the data set and see. Looks like we have an indicator for whether or not the Titanic participants who survived. And there's also a field for the ticket fare here. Now, this set a very interesting real world situation for me as I was setting up this example. I realized that when I was trying to do the hypothesis test, I was getting errors on data types. So I went back and said, okay, what are the data types I'm looking at? And what I found is that the fare had an object data type. And this didn't play well with the functions I was trying to use. So let's clean the data and convert the ticket fare to a numeric data. So just some code here. I did find a blank fare, which I think is what made the inferred data type an object probably. So I had to remove that blank and then was able to convert it to a float. I printed the data types again, and you'll see it's now a float, which will work nicely with these numeric tests. All right, so after the pre-processing, just from the basic exploratory data, which you may have seen in week 1 of the series, the webinar series, we can start into our hypothesis testing framework. So step 1 is to, again, define the hypotheses. We're looking for a difference or no difference. Survivors is S, non-survivors is N. Significance level 0.05. And now let's select the right test. So what type of variable is our input? Again, we're dealing with a classification of 2 groups, survivor versus non-survivor. So the answer is binary again. What type of variable is our response? The response is fair. So this is a continuous response. Is our response paired? No, the responses are not paired because, again, these are 2 independent groups, different subjects in this experiment. And is our data in both groups normally distributed? Or I should say approximately normally distributed. So let's take a look. Again, filtering to survivors first and then describing that group. Got a pretty decent sample size of 500. Mean of 1. Oh, I'm looking at the wrong, here we go, looking at fair, okay. Over here, mean is 49, and the median is 26. That's a big red flag that there's such a difference in the median and the mean. Take a quick look, the max is 512,
with the mean at 49 and the min is 0. Someone got on for free, I guess. So you see there's a huge difference in that. This is implying a significant skew in the distribution of fair. So let's run a test for normality. I'm using the Shapiro test here, passing in my continuous variable, the array of my continuous variable. The second value printed, and you can see this in the documentation of the function, is the p-value, very small, right? So we reject the null hypothesis that the data is normally distributed, and basically we're proving the alternative that it is not normally distributed. Therefore, we need to use a non-parametric test. There is no need now to test the other data group's normality, by the way. If either group fails an assumption test, then you just assume the non-parametric test. I did go ahead and go through, I did print the description of the other group just for visibility's sake. It's always good to take a look. But we see a similar thing. All right, so given all of these conclusions, the appropriate statistical test is the Mann-Whitney rank test, which compares medians rather than means. We're doing a two-tailed test because we're dealing with just whether there's a difference. And now we can run our test. So very simple, one line of code, passing in our survivor and non-survivor arrays of the fair. And it prints out a nice p-value here. Very small p-value, much less than 0.05. So we reject the null hypothesis. There is in fact a difference in fares between survivors and non-survivors of the Titanic. Very interesting commentary on societal class there. All right, moving right along, exercise 3. Be using a different data set called an ice cream data set. And I'm going to ask the question if there's a difference in the proportion of favorite ice cream flavors between females and males. Or said another way, is there a difference in the proportion of the gender between different preferred ice cream flavors? And then said another way would be, are these two factors of gender and ice cream flavors dependent of each other? Is there an implied dependency of these two factors? So let's take a look. We have an indicator of gender here, and we have a factor for favorite ice cream flavor. I did find later 1, 2, and 3 are the only factors here, the only levels. All right, so let's start our steps. The null hypothesis in this case is that the input and the response are independent. We're testing for dependency. And the alternative is that they're not independent, or that there is a relationship, there is a dependence between the two. Same significance level. And now let's ask ourselves, which statistical test are we going to do? What type of variable is the input? So since we're dealing with factors, both as the input and output, there's really there's not a whole lot of meaning, I guess, behind choosing which is your input versus the output, unless your question is such that you're trying to say that one influences the other. And of course, it's that secondary, what are you influencing, that is typically considered the response. But from a purely statistical standpoint, it doesn't matter which you choose as the input versus the output here. But let's choose gender as our input to say which gender group are you in, female or male? And let's choose the favorite ice cream as our response. So the input as the female versus male comparison is binary. What type of variable is the response? It's ice cream flavor, which is a categorical value. Another question that has to get asked in this scenario, which is described in one of the hypothesis testing flowcharts, is are any counts less than 5? Are we dealing with any really scarce data? We need to check. So we'll use a contingency table to see if there are any categories with counts less than 5. And in this case, it's interesting too, I'm not dealing with one or two-tailed because we're dealing with factors, both as the input and output. This is not a question in that scenario. So if you were here last week, you saw this similar structure of code, which is to do a pairwise table of counts for each factor. So now you can see kind of a nice contingency table of counts per group. None are less than 5. So that's important to note. Given all of these results, we will be using the Pearson's chi-squared test for independence. All right, and step 5 is to run our statistical test. The nice thing about a chi-square test for independence is all you have to do is pass in your contingency table, and it will basically compare all of the proportions and decide if there's a dependency. The way that this data prints out, the second value here is the p-value. So it's 0.1 greater than 0.05. So we failed to reject the null hypothesis. Ice cream favorite flavors and gender are independent. There's no relationship. All right, next exercise. I'll give some other different examples here. I'd like to know if there's a relationship between video game scores and puzzle scores in the same data set. I'll go ahead and scroll back up to show you those factors again, those variables. So you'll see here there's 2 columns that have scores in them, video and puzzle. And I found out from the data documentation, this means video game. All right, so we just want to know if there's a relationship. So we're going to say that they're not related in the null hypothesis and that they are related in the alternative hypothesis. 0.05 significance level. And now let's select the statistical test. So we're dealing with two numbers, right? Both of our variables have numbers in them. So since they're both numbers, again, are we implying that one impacts the other in a particular direction, or is it just, is there a relationship between either? It's more just that, is there a relationship between either, not trying to say that one influences the other in a particular order. So it doesn't really matter which you choose as the input versus the response. But for the sake of setting up the test, we have to choose one. So we'll put puzzle scores as input and video game scores as the response. They're both continuous. Now we have to ask for approximal normal distribution. Get to that normal approximation test. So let's go ahead and test the video. And our p-value printed here as the second item is less than 0.05. So their video game scores are not normally distributed in this sample. So we're going to use Spearman's rank order test for correlation. You may have heard of the Pearson correlation test. Spearman is the non-parametric version of that. Also, just a side note, if your data was ordinal and not continuous, like say you were ranking levels of ability into like 3 categories, like, you know, not skilled, somewhat skilled, very skilled, or something like that, then you would actually use Kendall's rank order test for correlation in that case. But we're dealing with kind of a numeric type of variable instead. So comparing 2 things, 2-tailed test, just trying to test if there's a relationship. Now let's run the test. So same package has a Spearman R function. We pass in our 2 values, and it will print out both your correlation coefficient as well as your p-value. So first I'm printing out the correlation coefficient known as rho, which is 0.48. You may have heard in testing in correlation in general that a value that correlation coefficients range from -1 to 1. And if your value is not 0 or like far away from 0, either negative or positive, then you can assume that there is some sort of correlation. What the statistical test does, though, is it says not only how strong the correlation is, but if there's enough evidence in your sample to say that that correlation truly exists as a broader truth, as a population. So what this is telling us is this correlation coefficient of 0.48 has a very low p-value and is significant. So we can say from a broader truth, from a population perspective, that puzzle scores and video game scores are related. There is an association according to this sample. So that's dealing with 2 continuous variables. All right. We just have a couple more. Exercise 5, is there a difference in puzzle scores between people with different ice cream flavor preferences? Kind of random, but for the sake of example, we're going to ask, okay, null hypothesis is there's no difference in the puzzle scores between the groups. Alternative is that at least one group is different. There is some kind of difference in puzzle scores between groups. 0.05 significance level again. And now let's select the test. So what type of variable is our input? We're dealing with multiple groups, which are people with different ice cream flavor preferences. 1, 2, or 3 in this case. So since we have multiple groups, our answer is categorical for the input. The response variable is puzzle scores. We're trying to ask if there's a difference in puzzle scores. So that's a response and it is continuous. Now let's ask, does the response follow a normal distribution amongst all the groups? So same activity here. In looking at this, data is not very skewed. Sample size is 95. It's reasonable to assume normality in this case. Let's look at group 2 of ice cream flavors. Same thing. Group 3. There does seem to be some skew here. Let's take a quick look. So mean and median, difference of 8. Min and mean compared to max and mean, there does seem to be some skew. So we'll go ahead and run it through a test just in case. And we see that there is a low p-value, less than 0.05. So we reject the null that the data is normal. Therefore, we cannot use a parametric one-way ANOVA as I would have thought as we were going through this originally, since the last group failed the test for normality, the assumption for normality. So the appropriate statistical test is the Kruskal-Wallis test to see whether the distributions are significantly different. So rather than comparing means directly with a one-way ANOVA in a parametric test way, we're using the non-parametric version, which compares the distributions between the groups. Deciding one or two-tailed when you're dealing with multiple groups, isn't really relevant. You're just dealing with, it's going to be two-tailed in a sense, no matter what, because you have multiple groups and you're just checking for a difference. One-liner again, you pass in your 3 arrays and you get your p-value, very small p-value. So there is a difference in puzzle score distributions between groups with different ice cream preferences. And you can, of course, do visualizations to try to understand more about where does the difference really exist. But a more traditional hypothesis testing approach to learn more about that is to do a post hoc test. So post hoc is basically a follow-up test that you would do after a hypothesis test when you need to drill down into differences between groups, typically. In the non-parametric world, we're going to use the Dunn-Bonferroni post hoc test to see whether these pairwise groups have significant differences in puzzle scores. So we already proved that a difference exists between certain groups, but now we want to know which groups are different. Did provide some documentation here. If you were doing an ANOVA parametric test, then the Tukey's honest significant difference post hoc test is what you would use. I did have to install a new package here. So I've included some code in case you need to do that. And we'll run the Pocock test. You have to pass in what your value column is. So our value is the puzzle score, and what your grouping column is, which is ice cream factor. And what you will get is a pairwise table of p-values. So now you can compare each group to the other group and see which ones are less than 0.05. So we can see that there's a significant difference in puzzle scores between ice cream flavor groups 1 and 3, and between 2 and 3, but not between 1 and 2. So if you look at the 1 and 2 value, the p-value is 0.06, almost significant, but not quite. If you compare 2 and 3, you'll see a very small p-value. If you compare 1 and 3, you'll see a very small p-value. That's kind of how you navigate that when you're dealing with multiple groups, but a continuous output. All right, and then finally we have exercise 6. Was cholesterol reduced after introducing a particular brand of margarine? We're going to ask about introducing margarine A in this case. So dealing with the new data set of cholesterol, and you'll see there are levels of cholesterol at different time frames. Before the introduction of margarine, after 4 weeks, and after 8 weeks. And then you have an indicator for which margarine brand they're using. I'm specifically asking about margarine brand A. So I'm going to go ahead and filter for that and take a look at that data set. So now I have my data set that is basically processed and cleaned according to my question. So let's define the null and alternative now. We want to know if the cholesterol after is less than the cholesterol before. We want to see if it was reduced. So the difference between after minus before, we want it to be negative, so less than 0. We'll set the significance level and select the appropriate statistical test. So the input is before versus after, 2 groups. So the answer is binary. The type of the response, we're going to use after 8 weeks just to allow for, a full amount of time for that effect to take place. It's just kind of an experimental choice of mine. And that value is continuous. So is the response paired? Yes, in this case, the response is paired because they're groups with before and after values and contain the same subjects in both. So they're not independently randomly different. They are dependent. Subject 1 has this paired set of variables, the before and after variable. So now let's ask about normal distribution, as always. Very small sample size here of 9. So that to me is a red flag. Let's go ahead and run a test. I do it for both groups, and I see that the p-values are greater than 0.05. So although the sample size is small, they're centered enough to assume normal distribution. Therefore, we can use a parametric test to compare means. So given these, we'll use a student's paired t-test to compare these means. Note, if any of your assumptions had failed in this case, you would use the Wilcoxon signed rank test. So now, since we're specifically testing for a reduction in cholesterol, we're dealing with a one-tailed test this time. And it's a lower tailed test because of the direction of the inequality being less than. So to run this, t-test rel is the student's paired t-tests in scipy stats, and you'll see a very small p-value. Since this is a one-sided test, you want to divide your p-value by 2. That's just a common step. Some functions will allow you to specify that as a parameter, but you'll get the same result either way. So you can divide this p-value by 2, still obviously very small, so we reject the null. There is a reduction in cholesterol after the subject started introducing margarine A. Great, so that's all of our exercises. That we have a couple more topics to go through, not as much in detail, but just to touch on. One is based on resampling and permutation testing. So using permutation testing to resample the data grants you the opportunity to present more evidence of associations or differences in your data. This is an example of using statistical simulation to provide additional evidence to your experiments. So consider the example of the margarine study, which is a paired study. We can generate what's called a permutation distribution by randomly assigning each subject's cholesterol to the before and after categories randomly over and over again. And each time you do it, you're going to calculate the mean difference for each permutation. Because of the inherent randomness of that process, the permutation distribution should have the mean around 0 of those mean differences of this kind of random assigning of cholesterol between these before and after groups. If margarine has no impact on cholesterol, we would expect that the observed mean difference in our original study sample to not be much different from this randomized permutation sample. So the permutation tests this hypothesis, and you can calculate a p-value. So basically, our observed difference is in the tail of our permutation distribution, which implies that there is very likely a difference here. It just kind of provides more evidence with another randomization and simulation technique. There's lots of different applications of this. And I've provided a resource here that I thought was really helpful in describing this concept further. Also, to provide additional evidence to your study are the concept of power and sample size. So power is the probability of rejecting the null hypothesis when in fact it is false. So we want to say it's a way to reduce the likelihood of a type 2 error. So it's a way to say, here's the result of our hypothesis test. Now, what is the probability of it not being a type 2 error, which is that you fail to reject the null even though there is a difference present. Power is usually represented as 1 minus beta. So setting a power is a way for researchers to know how many subjects they need to enroll in a study in order to optimize the ability to detect a difference should one exist. In statistical experiments, it is recommended that the minimum power to your study be set to at least 80%. Or in other words, 0.2, beta equals 0.2. What's really important to note is the underlying principle here is that as your sample size increases, so does the power of your study. There are many sample size calculators that you can use online to see how you can get to this power of 80, how many samples you need in your study, or how many subjects you need. So this is a common question in real world of clinical trial where there's a certain cost associated with enrolling more subjects in your study. So they'll basically ask the question, can we have a strong power, a very low likelihood of type 2 error if we only enroll 30 people versus 1,000 people? It's just kind of a way to get to that, what's the bare minimum we need as part of the cost of the study to still have a viable result. A lot of fun concepts in there as well. All right, and finally, we will cover A/B testing, which is a common application of statistical experimentation in the real world, I would say. Another kind of great real world example of this that's used all the time. It's often used in the field of web development. You might have heard A/B testing in the context of testing different UI designs for a website. You can assign a control group A to some website viewers and a treatment group B to another set of website viewers, and then directly measure and compare certain metrics of success and interest between these groups. For example, how many of the website viewers converted to a sale or converted, sometimes known as conversion rate, with design A versus design B. So here's kind of a visual example. You can set a control and then randomly assign certain website viewers to this other user experience and see if there's a difference in conversion rate, if there's an increase in improvement. And if there is, then that would be justification to change your UX design to that new structure. So here's an example. Imagine you're running a UI experiment where you want to understand the difference between the time spent viewing your initial layout versus a new layout. Let's say vertical layout versus a horizontal one. Imagine you're using average session time spent on that page, as your metric to analyze the result of your A/B test. So we aim to understand if the new design of the page gets more attention from users and increases the time they spend on the page than the old design did. So here's an example of a data set where we have viewers on the old design and their session time versus viewers seeing the new design and their session time. So let's go through our same steps in a very real world kind of way. So we'll define the null and alternative hypothesis. The null is that there's no difference in mean session time between the old and new designs. And the alternative is that there is. We'll set the significance level of 0.05. And now let's select the right test. So the type of variable of the input is another binary classification. There's control group A with the old design and your treatment group B with the new design. So the answer is binary. The variable of the response, or the variable type of the response, is continuous because we're dealing with that session time variable. Is the response paired? No, they are not, because the subjects are different between the two groups. They're independent groups. Are the session times normally distributed in both groups? Let's take a look. Mean and median are somewhat close, but you got to consider the full range of the data set. Close is a relative term, right? So 0.07 difference, that might actually be a meaningful skew in this case. Let's look at the min to the mean and the max to the mean. There does seem to be some slight skew, potentially. So to be safe, we'll do a quick test. And we see that the session time is in fact normally distributed because this p-value is not less than 0.05. Therefore, we'll do a student's t-test, two-sample t-test again. That's the assumption for now, but we do have to test the other group. And similar process, we see that we do not fail to reject the null that the data is normally distributed. So we can use a parametric test. Are the variances equal? Let's run an F test to find out. P-value is greater than 0.05, so we fail to reject the null. The variances are equal. So as we had thought originally, students two-sample t-test is what we'll use. We're just searching for a difference, a general difference, so we'll use a two-tailed test. Run our line of code from scipy stats, and we see a p-value of 0.21. So it's greater than 0.05. We fail to reject the null. There is no difference in the session time of the new design versus the old design. So this kind of thing is done all the time. We might have different experiences on different websites because we're subjects of an experiment for UX design. So this is happening all around us and is a fun example of that. And that's all I had today. Do we still have some time for some questions, Sneha? Oh, you're muted, Sneha.
I'm sorry. Oh, sure. We always have questions. Our audience are always asking questions. So we can do 3 more minutes of Q&A and close the session. The one question that I found interesting was, when do you do statistical analysis, right? Like, what is the perfect time? You have the raw data, and when would be the perfect time to do statistical analysis? So I would like to answer it by starting by saying that you actually have to do exploratory data analysis, where you look at outliers, where you look at missing data. So you want to handle all of that, like how Angela did in Titanic data set, where she found that the fair had a missing data. So it's important to know all of that beforehand before starting your statistical analysis. So handling outliers, understanding missing data, the data types. So all of this has to be done before starting your statistical analysis. And yeah, Angela, if you have any points to add to that.
Yeah, just that these data sets I used were already pretty conducive to just jumping straight into hypothesis testing. So yes, in the real world, definitely, you know, process and clean your data and understand it first. Yep.
Yes, and the other important question I felt is correlation does not mean causation. So that's a whole new subject that's always around of like, okay, did ice cream cause homicide in New York? All those questions. So whenever you see a relationship here, it means they are correlated and something is related to some other variable, but you shouldn't take it as causation, and there should be definitely caution over considering what is correlated versus what is a causation. Yeah.
Yeah, and I'd like to add to that, the ability to draw that conclusion of causation can be granted given the design of your studies. So if you're just looking at retrospective data and running a hypothesis test where you had no input on how that data was collected, then that's absolutely correct. You cannot, correlation does not imply causation. It simply applies some existence of an association. However, if you design an experiment and you control for any confounding variables with a control group and a treatment group, that's when you can make those claims where you can say, we've controlled for all other confounding variables, and therefore this correlation that exists has to be due to this one difference in these groups that we're introducing.
Right.
So those types of design experiments is what gives you the power to do that.
Right. And the last question for the day is, could you give an example, if there is one, where you would prefer a permutation test than a statistical test to assess the differences and similarity in data? This is asked by Diana, and thank you for your question.
Yes, thank you, Diana. I would say typically I don't jump to a simulation-based method. Because that involves resampling. So I would say if you have a really large data set that you're taking samples from for the purpose of maybe building a model, that might be a time where simulating resampling and doing a permutation test to check for associations or differences in your data makes sense. But if you're just dealing with, I have this small data set of 2 different groups of subjects and I want to measure some variable, you can't really simulate resampling that because you only have the one sample. So that's when I would choose hypothesis testing instead.
Yeah, that is a very informative session. Thank you, Angela, for answering all the questions and for like walking through us through all the 6 different examples. That was really nice. And to end today's session, I just want to talk quickly on the next webinar that's going to happen. It's going to be on regression and predictions. Please note that this notebook will be in R, but we have the same exciting content on starting from linear regression, a real world example, and then a lot of regression diagnostics of how to understand the data behind linear regression, and we'll end it up with polynomial and spline regression, and it's being conducted by Madhurima, and she is an amazing data scientist, and she loves volunteering for knowledge sharing sessions like this one. And yeah, as usual, join us through our Slack channels and other social media profiles. We have so many resources and so many opportunities for you to enhance your data science expertise. And thank you. Thank you for joining us today. We hope to see you again next week. Thank you, everyone.
Thank you all so much. Take care.